Without further ado, I will leave room for Raja for the first talk.
Yes, please.
Good evening, everyone. My name is Raja Senapati. I'm part of Netflix team, payments engineering team. Before we start, I just wanted to start with a story. The other day, I was, going with my son. I was dropping him off at the school, and that's usually the day when I give him all the important life lessons. So that day I thought, let me start with talk to him about traffic lights. So I told him, hey, son, do you know anything about traffic lights? He said, of course I know all about it. I watch you drive. I said, really? Okay, what do you know about traffic lights? It's so simple, Red is stop, green is go. I was happy. I said, okay, he knows. Yellow, okay. Yellow is you can go as fast as possible till you cross the line. Till the light turns red, you have to cross. I said, but what if I don't cross the line? What will happen when the light turns red? Dad, is that a trick question? If it is red, you have to stop, right? You press the brake hard. You have to stop at the line, right? Do you remember this head bump that I'm having? Yeah, I can see the head bump. You know what? I got it last week when you were driving. That's how I got it. I'm so proud of my son. He knows a lot about traffic lights, well, more than me, I guess. Okay, so the important thing is to know is, to start, when to start, when to stop, when to slow down, and when to, go fast. So at Netflix Payments, we found out this use case, a set of use cases where we thought it probably makes sense to, kind of slow down few transactions. And that's why we came up with this throttling engine. As part of today's presentation, I'm going to share it with you, just to make sure, everybody gets what we are doing with the throttling engine. So let's start. The question is, why do we really want to slow down? With Netflix going global, what we found out is, there are a lot of learnings, okay? One learning was not all payment processes are alike when it comes to scaling. Some processes, they can really scale well, give him any load and they're going to scale, they're going to perform. But some processes, they don't, right? So, and even without scaling issues, we were having, contractual obligations as far as our SLAs are concerned. We have to meet those SLAs that we have signed with those payment processes, right? So what are the typical, SLAs that we have signed with those payment processes? Hey, Netflix, you can only send us X transactions at any time, right? But by the way, between 12 to 3 at any time, you can only send us Y transactions, not more than that. Does that sound familiar? How do we make sure that we throttle those requests between X and Y between those times, right? So now there's a fun quiz. Whoever is the first person to answer this question gets a Netflix gift certificate. So can you guess what is the lowest concurrent transaction we support? One of our payment processors. Here, please tell me.
One.
Anyone else?
5.
Yeah, perfect. Who was the one to say 5? Perfect. Okay. All of you gets you, I guess. I believe it is probably there somewhere. I have it. Perfect, thank you. So imagine we have all these transactions ready to be processed. In fact, they're very eager to be processed. But we only have our processor says, hey, you can only process 5 transactions at any time, right? So how do you do it? How do we make sure that we only send 5 transactions and not more to the payment processor, right? So let's look at this problem a little visually, I love animation. So here we have our payments instances running on cloud. We have our client apps which expect to send transactions to the payment processor. And we have a processor, he who must not be named, but let's name him anyway, right? Processor 1. And let's just for this example, we set the SLA to 2, right? The rated SLA is 2. You can't send us more than 2 transactions at any point of time. Now you send the request to the payments, the client sends the request to us. And then as long as the requests are, within SLA, things are fine, People will say, okay, we are good. But the moment we exceed the SLA, things go bad. We get unpredictable response. We don't know whether that transaction is going to time out or it's going to, maybe we end up double charging a customer or do something, right? It's unpredictable. Nobody is happy actually, right? Oh, look at the clients, they're not happy. The processor says, how come you signed the contract? You said, send me 2 transactions. Now why are you sending me more than 2? They're not happy too. Look at us, that's us. We are not happy too, right? Okay, so what do we do? What solution options that we considered? So we explored a few options, queuing being one of them, but then not all our clients were tuned towards queuing. You use some kind of an asynchronous queue. That didn't work out for us, not in the current architecture, for sure. We also looked at things like a rate limiting proxy, but then it had security implications, single point of failure. We didn't like that either. So the third thing that we came up is Zookeeper. So this is something which you already use in a payment system, as part of our distributed, cloud architecture. But then we also use a concept called a pool of permits. A fancy name for this is a distributed semaphore. But for this presentation, I'm going to stick to this term, permit pool. More easier to understand, right? So the way it's going to work is, once you get a request from the client, instead of directly calling the processor, you try to acquire a permit from the permit pool, right? If it is successful, you send it to the payment processor. Right? Once the processing is done, you return back the permit. That's the whole principle. If you are not able to get a permit, you don't send the request to the processor. That's how it works. So let's extend this idea a little further, okay? Okay, so let's say there are multiple, concurrent transaction requests coming up. We have Zookeeper, we have the permit pool. Just note one thing. The permit pool size is same as the rated SLA that you see for the processor. It has to be the same. That's how we match, right? So you send a request to the client app, from the client app to the payments instance. One instance picks it up, grabs a permit, sends it to the processor. While it is in progress, in flight, another request comes in, grabs another permit from the permit pool, right? And sends the request to the processor. Both these 2 transactions are in flight, right? And you can look at it, we have reached the max SLA that we have with the client, right? And the permit pool is empty now. There are no free permits available. Now we get a third request. What's going to happen? It's going to send the request, try to acquire a permit from the permit pool. Permit pool typically has a wait time associated with it. If you are not able to acquire a permit during that wait time, you refuse it. You said, hey, this transaction cannot be processed. It's going to be throttled, right? So it's throttled. So from the processor's point of view, they only see a max of 2 transactions from us at any point of time. From the client's point of view, the good news is they already know how to handle throttle transactions because of our other use cases, we have agreed on. So they also get a predictable response. So they're happy. Usually what they would do is they'll retry those transactions later on, right? So they're happy too. And then, because both of them are happy, we are happy too, right? We're all dancing. Okay, now let's extend this idea even further. What happens if a permit is being returned back to the permit pool, right? So we had 2 transactions in flight. The processor is seeing that we have reached the max SLA. The permit pool is empty. The third request comes in, right? And then it's trying to acquire a permit. Usually the wait time will be like 2-3 seconds, which is configurable. But during that time, let's say request 1 returns back the permit because it has stopped processing, right? So that request, that permit will be reused. It will be acquired by the third instance, the third request. And then it goes to the payment processor. So now the payment processor sees again, two requests, right? So they are happy too. And eventually, once the request is processed, it gets returned back to the, to the permit pool, right? And eventually, all requests, once they finish their processing, they return all these permits back to the permit pool, right? And everyone is happy, of course. Okay. Now, what's the technology stack we use for this? Of course, we use Zookeeper for distributed coordination. We also use a framework called Apache Curator. So this is a framework which is actively developed and maintained by Netflix. It's an open source framework. You can also use it. It gives you a higher level constructs. We call it recipes on top of Zookeeper. So for example, it gives you things like a leader selection in a distributed environment, distributed queue, and the recipe that we are using in our project in the throttling engine is called shared semaphore, which gives us the ability to develop and maintain the permit pool in our system. Okay, all this is fine as a concept, but how do we implement it? So this is the code snippet. So if you look at it at app level, initially we create a curator framework client, which knows how to connect to a Zookeeper cluster. Then at the point of activation, we decide, hey, now let's throttle this processor. So you create a permit pool, which is essentially an interprocess semaphore. And there you pass a representation of the processor that you want to throttle. You also pass the SLA. Like for example, in the previous instance, we wanted the SLA to be 2. So you pass 2 there, right? Then at each request level, what you do is you try to acquire a permit. If the permit is acquirable, it is acquired within the given timeout, then you let it go through. If you can't acquire it, then you mark it as throttled. And then finally, you return the permit back to the permit pool. Very simple concept, nothing complicated. The good thing is our throttling engine is implemented as an interceptor. So what it means is it intercepts the processing pipeline, right? Very transparently. So the processing pipeline doesn't even need to know that the requests are being throttled, right? So that gives us a lot of abilities. So for example, we could say, hey, let's throttle this processor in Mexico between 2 o'clock to 5 o'clock only for renewal transactions, right? And let's just constrain it to like 10 transactions at any point of time, right? We will allow only 10 transactions. So it is just a bunch of fast properties that you create at the runtime. You don't have to change any code, a single piece of code. You don't have to deploy any new code. You don't have to bounce any instances. So that's the kind of ability it provides. And let's say in the unlikely event Zookeeper is down, it also gives you ability like throttle everything mode or throttle nothing mode. So that while you are attacking the issue, zookeeper issue, your clients get a predictable response. So that's pretty much it, I guess. Thank you.